and we can get going with this. Again, really happy that you could join us, Rui, for this, and that we have a possibility then to connect and, have others join us and share in. I see a bunch of people joining us now. So thank you again for being able to do this. It's really, really good. Simon, if you said something, I think I saw your lips move, but I didn't hear a word, so
No, I didn't say something. Thanks.
Oh, gotcha. Okay, I wasn't sure if it was intentional or do a plan. Good. Okay, I think a couple more people are joining us now. That's great. I'm just going to start sharing the screen, Rui. So we're
Okay.
on that. Everybody knows where we are. Great. Okay. So let's just wait another minute and then we can get going. Hey. Okay, welcome everyone to today's presentation by Dr. Rui Zhu on bridging geospatial semantics and GeoAI. My name is Francis Harvey, and I'm happy that we could have Rui join us today for this session that we're organizing through the Geospatial Semantics Commission of the International Cartographic Association. I just wanted to say a few words about that because it is a new series that we're going to be holding regularly. So I wanted to just share ever so briefly while we're just for a minute before we move to Rui's talk. It will take place about every 2 months. It will be only online, and the sessions are going to be video and audio recorded for publication at the ICA Geospatial Semantics Commission website. The main purpose here is to help in connecting researchers working on cartographic and geospatial semantic research themes. And in that sense, we can look forward already to the next talk on the 5th of February, if you want to put a note in your calendars or online, for a talk by Dr. Dalia Varanka from USGS. The title and abstract will be available shortly. I only have one very, very brief note about the organization of today's session, and that is if you have questions, I'd ask you to please raise your hand using the Zoom function, and you'll get into the place for a verbal question after Dr. Zhu has finished his talk. Or, of course, you can post questions or comments in the chat. Please remember the presentation and discussion are being recorded. Finally, all I want to do then is introduce today's speaker. Dr. Rui Zhu is a lecturer, equivalent of an assistant professor in spatial data science at the School of Geographical Sciences, the University of Bristol in England. There, he is also the director of Geospatial Data Science and Spatial Analytics program. Broadly speaking, he studies how humans and machines organize spatial knowledge and how such a process interacts with the environment. More specifically, Rui combines theory-informed, for example, geography and semantics, and data-driven, for example, machine learning and spatial statistics, approaches to address geospatial challenges such as geospatial data interoperability, spatial predictions, and spatial reasoning. We're going to just move right away into Rui's talk. I just want to say, should there be any technical difficulties along the way, you can already find a copy of the presentation slides at the Commission website. The URL in the shortened format is there above. That's all from me. I'm going to hand it over to Rui now. Rui, you have the floor. Thank you again.
Thank you so much, Francis.
Let me just share my screen. All right, can you see my screen?
Good. Yes, it's all good.
Okay, cool. All right, thanks a lot, everyone. It's my pleasure to be invited to present my thinking and also research in this exciting field about bridging the geospatial semantics and the GeoAI. And before I delve into the contents of this presentation, I have to confess that I'm gonna mention some of I checked the participant list. I'm gonna probably mention some of your work here, but if I explained it or interpreted it in a wrong way, please forgive me on that, and you will see it in the later of my slides. So first of all, I would like to give you an overview timeline on where we are and where we were for the geospatial semantics and also GeoAI. And so here is basically a timeline I created that represent the different stages of our domain has been developed. By the way, this is advised by several papers. I know that this doesn't represent the whole landscape, but I hope this picture can basically briefly represent our domain. So back into the 1960s, we have, where the behavior geographies arises, and then we have GIS system, and then we have spatial cognition, which emerges during the 1980s and the 1990s. And then with all these theories, like when we have the field, which is called GI science, was established. And after that, a lot of people focused on the ontology and the semantics of representing and reasoning over geographic information. And after that, we also have linked data, and specifically, we borrow that kind of technology to represent linked geospatial data. And this kind of historical flow actually was caused by development of new technologies. For example, in the early 1980s, we have the microcomputers, which basically helped us to create the transfer from GIS system to GI science. We wanted to better understand how humans understand and represent maps in their tablets or on their personal computers. And also we have symbolic GeoAI or GeoAI developed it also during this period of time. And we have database technology, semantic technology, and also we have big data or social sciencing emerging during the 2010s. And now we have this kind of connectionist GeoAI. Also, I want to categorize them into three big functional areas, because usually at the very early stage of our community, most of our tasks are to help people to find the ways, basically how to navigate, how to find how to do wayfinding. So that's actually where cartography or maps was emerged. And during that period of time, most of our semantic models are the cognitive models of our geographic space. And then after that, with the database and also the GI science emerges, we are more interested on semantic interoperability. This is where the geospatial ontology and the geospatial semantics actually emerges. And build on top of that, we moved on to finding out how could we improve the integration, which actually is a little bit different than interoperability, because the integration is more complex. It involves things like question answering. It also involves things like knowledge management by the big companies. And during this period of time, we combine the symbolic AI with also the connectionist AI to do this. So basically, this gives you an overview of the timeline. And in my talk, what I'm going to do is I'm going to identify pieces of seminal works during different stages of this historical line. And at the end, I'm going to propose some new ideas or new directions I think we should focus on, or these can be our opportunities for our community to grow. So first, I'm basically focusing on some studies all around the 1990s or before 1990s. And this is all based on one seminal work by Mark. The paper was written in 1990s. The title is called Cognitive Models of Geographical Space. And in this paper, they systematically summarized the cognitive models of geographic space before the age of 2000. And they summarized also the seminal works about the cognitive models in geographic space, including the classic work about images of the city, mental maps, cognitive maps, AI in geography, and so on. And these are very good review paper, but at the end, I believe the key finding can be summarized in this one sentences, meaning that the mental representations of the geographic world are not stable. Rather, they seem to be constructed for a particular goal, drawing from multiple sources from scattered information. So at this stage of our community, the researchers mainly focused on the cognition and psychology work, and there's no or few like formal representation of these kind of cognitive models and implement them into GIS systems. And also in that paper, it's quite interesting that the authors identified 3 high priority cognitive research directions that people should focus on during that period of time. And I listed them here because I feel some of them we answered, but some of them we still barely answered. And I listened here just to give us a review that we still like 30 years past, we probably still haven't answered all these interesting and very important questions. So they identified these 3 directions here. First is the formal concepts of geographic details. And here they specifically mentioned, is the skill more important in the physical domain than in the human or not? And what skills of representation lend themselves most to visualization and to other forms of representations too? And what types of data are most amenable to display at scales? And I believe many of these questions have not been answered at the current stage, even though we have more advanced technologies. And also they identified the cognition of dynamic phenomena and their representations. Basically, it means like how could we represent the process or procedure in geographic phenomena. And these kind of models, I feel currently, we barely see them, for example, in S-rays, GIS systems, or any other types of systems. And also they recognize that the multiple modes and the multiple frames of reference for spatial knowledge is an interesting and important direction. And nowadays, if you are familiar with the computer science or GeoAI research, you still recognize like how to incorporate multimodal data into AI. That is still challenging. And so many of these questions, we still don't have an answer, even though we have advanced technologies. So also at the end of this paper, Mark and others, highlighted that the field, this field over geospatial semantics, or you call it the cognitive spatial cognition, it really is a combination of different disciplines. For example, geography and cartography here provides concepts and relations for geographic space, and the cognitive and environmental psychology provide empirical investigations and the models of human factors. AI provides formalization and computational models. As you can see here, they specifically mean basically the symbolic AI. And as well, it also provides ontologies and structures for the development of cognitive models. And the linguistics specifically provide a link to the construction of descriptive spatial phases and the use of spatial metaphors. And also philosophy provides a theoretical foundation for spatial concepts. So really, we are really an interdisciplinary field here. Actually, the reason I put it here is I see like Francis in his description of this series of talks, he specifically highlighted that we wanted to bring multidisciplinary research into this series of work. So that's the reason I wanted to highlight this, that from very, very beginning of our fields, we highlighted these points. And so that's the very beginning of where we are. And after that, during the 2000s, a group of people mostly focused on ontologies. And the context here is like we have a lot of database systems, and researchers need to study like how could we better model spatial and temporal data in those databases. And then it boils down like how do we model the ontologies. And Frank, as a seminar work here, explored the minimal set of ontological commitment in this work. And he mainly do so from a spatial temporal database construction perspective, meaning that is how could we build a better database system that can serve information retrieval. And his work actually was developed on top of the 3 levels model in the analysis of macro world proposed by Davis from 1990s. I believe most of us are here probably familiar with this model. So we have the domain model, which we can also call it a conceptual model. Based on this domain model, we will build the axioms, which will be logic model. And after that, we will have the implementation, which will be the physical model. And based on these 3 levels of model, he actually introduced this very interesting 5 tiers of geoontology. I would say it's a framework for ontology engineering in geography. And we have like a physical reality. How do we model physical reality? And on top of that, once we have the observations, how could we model that? And then how could we reflect that back to the object in the real world, and how these kind of objects are interacted in the social reality. And at the very top level, how human beings perceive this kind of social realities. So this, in my opinion, provides a very good guidelines for any geoontology engineers to build a feasible and interoperable ontology for GIS. However, my experience here is like we barely use it. There are many reasons I feel, but I will talk about this more in the next few slides. But my experience here is like, we barely use this kind of series really to get our practices in ontology engineering in our real life. So that's Frank. And after that, actually, Werner Kuhn actually has another seminar paper about the geospatial semantics, why, of what, and how. And in this paper, he highlights that the reason we need semantics or ontology is for us to achieve the interoperability goals. And interoperability here can be defined as the ability of systems to provide services to and accept services from other systems, and to use the services to exchange to enable them to operate effectively together. And semantics here refers to the attaching meanings to language expressions. This is a conceptual phenomenon, and he borrowed the semantic triangle to explain this to our geospatial semantic field. Like, we have the entities in the real world, and then we can use a symbol to represent this entity. And by using this symbol, humans actually have a perception or have a conceptual notion in their mind about the entity. So this has 3 entities, 3 notions here actually comprise this kind of semantic triangle. So this, I believe, set the foundation for geospatial semantics for our later works. And again, in Werner's paper here, he also talked more things here. For example, geospatial data and services contains symbols, which meaning is not only a matter of convention, but grounded in physical reality. So here, he basically distinguished the geospatial semantics with semantics. So we could say this is our version of why geospatial is important here for semantic studies. So the first one is we have the grounded truths or grounds in physical reality. The second point is here is like geospatial information is often based on human perception and social agreements, and so that it combines the both objective measurements with some subjective judgments altogether. So this is also which makes our systems usually very complicated. And he also mentioned a special case of social agreements are the geographic names and other identifiers of geospatial entities. This is where all the studies of gadgetiers comes in. And beyond that, we have space-time are primarily understood through processes. This is where, I mean, we also need a model to model the formal model to represent the processes, which we don't have enough work on that. And lastly, he also highlighted that vagueness, the importance of vagueness, uncertainty, and levels of granularity. And all those are also fundamental for geospatial information, but those are not necessarily needed for the general types of semantics. So this is what makes us unique here. Why geospatial semantics are worth to be really stand as a unique field here. And in that paper, he talked about the semantic reference system. I still believe this is a very innovative framework or idea, which we field of work, especially for current days, have followed up. So basically, the idea here is semantics-based GIS are about reasoning, not only about ontologies. So usually, even for nowadays, I feel like while we're talking about the geospatial semantics, it's mainly about mostly about how do we develop an ontology so that it can better represent the information we have. And then they can be integrated all together. But we less care about the reasoning. But in order to have a reasoning here, actually, Werner proposed that we can have a semantic reference system, which is an analogy of the geographic coordinate system. And by saying semantic reference system here, this is actually a conceptual coordinate system that can support the computation of conceptual distance and similarities. And in addition to Werner's work here, I also included a book. This book is called Conceptual Spaces, written by Gardenfors in 2000. In this paper, he also talked quite a lot on how could we build a conceptual space and how could we do computations that all about do computations on top of concepts. So I believe all these ideas are still even though they were introduced in 2000, but we, at least in our field, we barely implemented them yet. And by offering semantic reference system here, actually we offer representations and reasoning capabilities for four things here I'm listed. For referencing, for example, we can referencing symbols to concept specifications. And usually we can use ontology to achieve this. And we can also ground the concept specifications in physical reality, because as my previous slides indicated, grounding is really a uniqueness of our field on geospatial semantics. And Werner in his paper mentioned a technique called image schemata, which was developed by several early researchers in psychology. And he proposed we can use this idea to do so. But again, actually, for these days, I feel we don't have much work on this, especially how to combine that with GeoAI. And the third one is the projections. And also the fourth one is about transformations. It's more in analogy to our geographic coordinate system. It's like how could we project the concepts and also how could we transform the concepts from one space to another space. And I believe that by combining Werner's work with also Gardenfors' conceptual space work, we might achieve this. So these are Werner's work. And I also wanted to highlight the image schemata a little bit in case you haven't heard about this. So image schemata here is the possible base interactions of humans in the world. And people believe that these kind of interactions are actually simple and limited, and their meanings can be captured as image schemata. And the more complex and the more abstract concepts humans are capable of or can be combined or can be represented using those base concepts through transformation or projection, I think. And I think both Frank from his 2003 work and Kuhn from his 2005 work proposed to use this idea as the ground for our geospatial semantics. Because many of the schemas are spatial and process driven. For example, like the container, like the path, this kind of schemata, they are all spatial, and they are universality across languages, meaning that no matter you speak Chinese or no matter you speak like English, this kind of very basic conceptualization won't change across cultures. They are because they are very basic ones. And they also have the cognitively fundamental roles on building more complex concepts. So based on these kind of benefits, both think that Frank and Quinn think that they can be the foundations for us to ground the geospatial semantics. However, the question here is, again, as I mentioned, how do we formally represent an image schemata in order to invoke the intended interpretation? This is still an open question. Right. So all these are, I believe, are set our foundations for geospatial semantics from a very high level. And then I move on to the stage around like 2010 to 2020. So where we have new technologies coming in, such as big data, such as social sciencing, such as semantic web, these kind of new technologies. And there are several papers that was written by Yanovich. And here, one of the papers is about the geospatial semantics and linked data spatial and linked spatial temporal data. And in this work, they basically adopted the semantic technologies to better represent the spatial and temporal data. And they found that the geographic information actually is a critical part of many central hubs on the linked data hub. And in the paper, this is also a high-level paper. They identified several major research directions, including geo-ontology engineering, including semantic reference systems, that as my previous slides, and also the semantic primitives and the information grounding. I believe this aligns to actually the image schemata idea that I showed you on the in the last slides as well. They also propose like event discovery and spatial temporal ontologies. I believe this is also relevant to the process. How do we model process? And they also propose that place is also important, and how do we model place? And also similarities, alignment, and translation. And here I highlighted 3 of them because here, based on my experience on reading all the literatures during this period of time of the work, I feel that many of the work, emphasized on these 3 directions, while giving less weights on the other 3. Namely, that I found more research papers focused on geo-ontology engineering or developing place-based GIS, or developing some like trajectory ontologies and trajectory analysis for mobility study. And also there are quite a lot of work using the machine learning or deep learning to compute the similarity of the embedding, similarity of different place types and so on, and then do alignment. But we barely still see a concrete work on how to use the semantic reference system, how do we build semantic primitives, and how could we model events or model these kind of spatial temporal ontologies and use them in real life. So that's the landscape for this stage of the work. And another, talking about linked data, I can't avoid talking about the knowledge graphs here. So during this period of time, knowledge graph emerges, and a lot of research groups started to investigate how knowledge graph could help us better represent both qualitative and quantitative geographic information, because the community believes that knowledge graph compared to the relational databases, it emphasizes more relationships over attributes. It connects data across things and silos, rather than just storing them as different spreadsheets, and then you need to use table joins to join them. And also it breaks the data and the metadata distinction by making data really smart, so that you don't need to check the metadata for data, which is often stored in a separate file. You can just get the understanding of the data by just looking at the data as a whole. And also knowledge graph is machine readable. It contains rich semantics, and it also enables conflation and inference. And most importantly, it is also impressive, extensible, and flexible. And it also aligns with the FAIR compliant, which means it is findable, accessible, interoperable, and reusable. So at the end, it is capable of supporting not only interoperability, but also integration, because we can really build question answering systems and use the knowledge graph to also help large organizations to organize their heterogeneous knowledge or geospatial knowledge base. So by using this kind of technology, we are moving from really interoperability to integration, which is more complicated, which is more intelligent. So that's knowledge graph. And since I worked on for my whole postdoc, 1.5 year postdoc experience, I worked on this project called the Nowhere Graph. So here I'm gonna give you a little bit on this specific project, how we use knowledge graph to better organize scientific data. So this project was funded by NSF, and we basically focused on connecting environmental and human-related scientific data observation altogether, and using the concept of space and time, which is a key concept in geospatial semantics again. And to increase the reusability of our graph, we basically make sure we use the international standards as much as possible. And we used the sensor observation sample accurator ontologies. And also we use the time ontology and the geospark ontology. And of course, built on this, we also built our own ontologies. For example, we built an ontology basically to represent the different types of regional identifiers, which I don't have time to delve into it, but hopefully this gives you an idea of how could we use knowledge graph to basically increase the integration capability of our data. So beyond that, next slide here. Beyond that, all sounds actually more about the symbolic modeling, meaning that we design ontologies to better represent humans' understanding or perceptions of the geographic concepts, and we define their relationships through symbolic approach, through logic. And on the other spectrum of this research, we also have the sub-symbolic AI or sub-symbolic approach, which meaning that we represent those kind of concepts using numerical vectors. And here I'm going to introduce you some of these seminal work during the past 10 years. The first one I'm going to introduce you here is called semantic signatures. And this is mainly developed by my PhD group, STKO, back to UC Santa Barbara. So the core idea here is that we created these semantic signatures as an analogy to spectral signatures from remote sensing, and we hope that these kind of semantic signatures can can capture the humans' perceptions of the different geographic concepts in a quantitative way. And by doing so, we actually define 3 groups of semantic signatures. And here it includes spatial signature, as I'm going to show you here. Basically, what we did is we used spatial statistics to understand how different POI, point of interest, across different gadgetiers, across different data sources, how they are, what they look like. And for example, here I show you, I used replace K, which is basically tells us how clustered when a site of points are. And I use that technique, that spatial statistic on points about on the top, this is actually a park. On the bottom, this is actually dam. So then you can see here, based on this kind of characteristics from this replace case curve, you will see that the semantics of park and the dam are quite different. So here, the core idea in summary is we use the spatial statistics to help us capture the characteristics of the data about the park and the dam. And then we use this kind of statistics on the data to represent the semantics of the place type. This is spatial signature. And similarly, we created a temporal signature. For example, like, how often people check in different times of the week. to represent the different place types. And as what I show you here is like this is basically the signature for restaurants across the whole week. If we compare this, for example, with probably parks or probably schools, their signature is going to look quite different. And meanwhile, we also have the thematic signature, as I'm showing you here, as a cloud, word cloud as one example. You can see what people talking about different, Asia restaurant and stadium, people using different words, and we quantify them as a quantitative vector so that we can basically compute their similarities or compute the distance of different concepts. So that's the semantic signature. And then I want to, all this, can be encapsulated in a concept called embedding. So if you work on AI or machine learning, maybe this term sounds more familiar to you. So the core idea here is, as I mentioned, we want to represent the symbols, for example, like place types, like restaurants, as a high-dimensional quantitative vectors. And basically, there are two approaches of representing them. One is to use like this kind of domain knowledge, as what I'm showing here, like the semantic signatures. And another way is to use machine learning. So our lab also have a seminar work on using specifically natural language processing technique to embed different types of place. And basically, the idea is we use the model called word-to-vect, and we adopt that model and make sure that the model can consider different spatial interactions of places, so that can basically capture the interactions between different POIs in the space. And as you can see here, we have two streams of doing the embedding. One is really using the spatial statistics or using our domain knowledge of doing this kind of embedding. This kind of approach are often explainable, but usually computational intensive. However, by using like this kind of machine learning methods, the downside is it's not explainable because all the embedding, the dimension of the embeddings, we don't know what's the meaning of them. But altogether, they can still capture the semantics or the similarities between different concepts. And the good side for this kind of machine learning methods is that they don't need too much computation powers once they are trained. So here, the idea is the embedding methods enable the investigation of theories on cognitive space, semantic reference systems, image schemata. But how to do so, that is still an open question. So then I wanted to delve into the next part, which I, align with my title of this talk is how do we bridge this geospatial semantics and GeoAI? And here I wanted to answer basically two types of questions, hoping to give you some ideas of how to do so. First is how could we leverage theories from the geospatial semantics or from the spatial cognitions to help us better develop the new GeoAI methods. So that's one interactions between these geospatial semantics and the GeoAI. And another type of question is how could we adopt the GeoAI models to uncover maybe new insights or maybe new theories for geospatial semantics? So we did a little bit of work on this. And for the next few slides, I'm going to share with you our very initial experiments on this. So first is how do we leverage theories from geospatial semantics to the development of new GeoAI methods. And this is our work basically to represent and reason over high-order relations in knowledge graph. And so the problem is like this. So while we're using knowledge graph, the nature of knowledge graph is basically to represent the pairwise interactions. For example, A overlaps with B. This can be readily represented using triples or RDF triples, node edge node using knowledge graph technology. However, in geography or in geospatial semantics, we usually also use higher order spatial relations in our daily communications. For example, we would say like this: Taihang Mountain is between Shanxi province and Shandong province in China. Sorry that I use this example because this is my hometown. So how do we represent this kind of high order relationship, such as between, which involves more than two relations? That's a challenge. And in fact, actually, in our geospatial semantic literatures, there are already very comprehensive work on reasoning and also on, basically more from logic part of reasoning ternary project relations, like what type of ternary relations we can have, and what are their interactions with each other. So, however, we still don't know how to represent them using this kind of new technology, such as knowledge graph. And in this work, actually, what we propose is we use the reification, the technical reification, to model those high order relations. And the core idea here is we create a new class, and this new class can have several rows. And these different rows will link this class or node of this class to different places, so that more than two places can be involved in this specific relationship. And one example is showing on the right side, which I'm going to use in the example from Santa Barbara. Sorry, again, I'm a geographer. I use all the examples across the world. And this example shows you, like, for example, here, Los Angeles, here, Southern Oaks actually is between Los Angeles and Ventura. And Santa Barbara is before the route where you travel from Ventura to Los Angeles. So by using this kind of ontology patterns, we can basically represent this kind of higher order spatial relations. So now we addressed the representation problems. Next one is how to reason over them. So even though that we have the logics from our spatial cognition literature on how to do this, but though usually these kind of methods are very time consuming and they can't take into account the noises in your data. So here we propose a connectionist way of modeling or reasoning over ternary projective relations. So basically, what we do is we transfer problem to our prediction tasks. Basically, what we wanted to do is we wanted to predict the spatial relations or predict the place. And one example for the spatial relation prediction is here. What is the spatial relation between Santa Barbara, Ventura, and Los Angeles? And for example of place prediction here is like what you can ask, which city is on the left side from Santa Barbara to Southern Oaks? So basically, we transfer the reasoning task here into link prediction problems for knowledge graph, hoping that using the technique from link prediction, we can answer the spatial reasoning questions. And here is basically the base model we adopted for this task. Again, due to the time limits, I won't delve into the details. But here, just to give you an idea, is we organize the tuple of the high order spatial relations into 3x(n) matrix here, and then we do a little bit like a convolution and also Fully convolution layers, and then we compute their relatedness among all these different row value pairs. And based on these relatedness scores, we compute the compatibility scores of each statement. And if the compatibility scores of one statement is high enough, then we would say this statement is true. Otherwise, we would say this statement is false. And by training this model, we use logistic regression because we regard this at the end as a classification problem, as whether that statement is true or that statement is false or not. And to allow my model see, both true examples and also false examples, we use the technique called negative sampling to make sure that my models, in addition to see a lot of training data, labeled training data, but also meanwhile see a lot of like false data sets, so that it can better build the boundary between true and false. So that's the basic idea of this. But my focus here is wanted to tell you that this model, this original baseline model, is not spatially explicit at all. So even though this works on the high order spatial relation knowledge graph, but it does not have any specific components that consider spatial or series from geospatial semantics into account. So my next work here basically is asked to ask how could we leverage the series, for example, from geospatial semantics, and then we leverage this kind of series to help better improve the performance of our baseline model here. So here we identified 3 types of series that we can apply. The first one is a strictly high-order relatedness. The second one is a mutual exclusivity. And the third one is a conceptual neighborhood. And again, due to the time, I'm going to introduce 2 ways of doing this from these 3 approaches. And if you're interested on the full picture, feel free to read our papers. So first one is strictly high-order relatedness, and what it is. So basically, in general, high-order relations for knowledge graph, usually this kind of high-order relation can be decomposed to a set of pairwise relationships. For example, here I have one example. Maria Curie won the Nobel Prize in 1903 together with Henry and Pierre. If we decompose this or simplify this into a pairwise relation, saying that Maria Curie won the Nobel Prize in physics, such a statement is still valid. So that definitely works. However, for our high-order spatial relations, such as Ventura is in between Santa Barbara and Los Angeles, if we compose them into pairwise relations here, such as Ventura is between Santa Barbara, such a statement actually becomes semantically invalid, meaning that all these 3 components in my high-order spatial relations, they are simultaneously involved. They cannot be decomposed into 2. So then, based on this knowledge, what we did is we go back to the architecture of that baseline neural network I showed you. We changed the component where we compute the relatedness of the row value pairs here. So originally we only compare them, pairwisely, but in this new framework we compare, all together in this kind of sequences. So this is how we change the model. And later you will see this can definitely help us improve the performance of the reasoning. And another example is to using the conceptual neighborhood. The conceptual neighborhood, in case you haven't heard about this, this is more about to model the direct discrete transitions between temporal and spatial relations. And specifically to ternary projective relations, we have this side of conceptual neighborhood. For example, left will be more easily confused with before, after, and between for humans. It won't be confused with, for example, right in this case. So based on this kind of domain knowledge, we basically use it to refine our negative sampling strategy. So the idea is like a relation is easier to be confused with its conceptual neighbors. So different samples from the conceptual neighbors will be intentionally selected in my negative sampling process for the training, so that I make sure my model was trained using really difficult samples. So that's the hypothesis. And we did a bunch of experiments, and we removed this component, removed that component, and try to see how these kind of different types of series play roles in our model. And here is the results. And I will not delve into the details, but in general, it tells us that spatially explicit methods, that as I introduced you here, can win quite a lot. Usually can improve the performance of the reasoning about 20% for our model. And we can use these kind of methods for geo-knowledge compilation, geo-question answering, and also delineating negative cognitive regions, these kind of applications. I see Francis, so maybe I'm running out of time. Yeah.
You have 2 minutes left.
2 minutes, okay. So I'm gonna be very quick. So next one is actually how do we adopt AI methods to uncover insights and theories for geospatial semantics. So I won't delve details. I'm going to give you an overview of this work. This work was done by my colleague Ling Cai, who's right now working at IBM Research. Basically, what we did here is we use machine learning techniques, basically to build the relation graph construction. And basically, from this relation graph construction, we can recover the conceptual neighborhoods graph. And this is the results. This is the results learned from, on the left side, these results learned from some machine learning methods using the embedding I introduced you. And on the right here it is our conceptual neighborhood graph. And as you can see, they are quite similar. And meanwhile, we found that by using machine learning, and this is mostly trained on data, it can also learn the symmetric similarities between relations. This actually aligns with our colleagues' work, for example, like Klipos and Mark's work on that, the topological relations, their similarities are not symmetric. And DC, for example, here is more similar to EC than EC to DC. So this kind of work has not been solidly proved in human or spatial cognition, but we used the data-driven machine learning methods. We proved this is possible. Summary. So I wanted to summarize that, highlight that we are a field with rich series, even though nowadays you probably heard a lot, yeah, we don't have series in this kind of AI methods. We don't see our values in this, but I strongly believe that we do have series. It's just sometimes we forgot those series that are developed by our pioneers. And but I would agree that there is indeed a big gap to bridge such series with state-of-the-art AI methods. And I hope through this talk, I showed you that we can use knowledge graph basically here as a technology to represent the geographic information based on some series in geospatial semantics. And meanwhile, we can use spatially explicit machine learning to potentially help improve the performance of general machine learning methods in addressing geospatial challenges. And meanwhile, we might uncover knowledge leveraging machine learning as well. And for some discussions, which I don't have answer for all these questions, but I hope this can trigger some discussions at least, probably. Sorry, technology. So first, so many this kind of theoretical and conceptual ideas proposed in geospatial semantics have not been fully explored yet, as I highlighted or mentioned many times already in my talk. For example, how to represent the vagueness, uncertainty, and levels of granularity to enhance human-computer interactions. For example, right now, like the ChatGPT, like all these kind of fancy generative models, they won't be able to model these vaguenesses, and they only give you an answer with certainty. But this how much we should trust them is always a question. And secondly, how could we implement the ideas such as cognitive maps, cognitive atlas, cognitive collage, cognitive graphs, and conceptual space in computerized systems. So we do have solid series in these fields. We have done a lot of experiments on human subjects, understanding how human build this kind of knowledge. But we don't know how to transfer this kind of knowledge to computers to make AI systems, and also how to formalize image schemata. And I think maybe we can use it to represent place. In fact, I had a discussion with both Jano and Werner before, but probably I think this is probably with knowledge graph technology, with AI, probably this is also the time to pick up this topic. And meanwhile, how to test and hopefully further build the geofoundation models that adopt the series from geospatial semantics. By saying that, I mean two perspectives. First, we can use this kind of series to have a systematic criteria or framework to evaluate the foundation models, to really justify whether the model can only memorize the language or it can really reasoning. So we can use this kind of series to prove this. And secondly, I believe if we can have this kind of knowledge and better use them, maybe we can build some small language model, sorry for the typo there, but maybe we can build some small language model that is equally powerful as larger language models but it is meanwhile more explainable. So I hope you enjoyed my talk, and I listed all the references here I mentioned in this talk. And feel free to reach out to me if you have any ideas or collaborations or comments. And I'm also happy to answer questions here. Thank you so much.
Thank you very, very much, Rui. That was really a wonderful talk. Really, and really, I can't emphasize how wonderful it was as a talk. We went a little bit into our time for questions, so I don't want to take any more time before I ask if anyone has any pressing questions they'd really like to let go of and use the opportunity for a discussion right now. Don't see any right now, so I'm going to ask you a question, Rui. You're going to probably not be surprised by this question at all, given what we were talking about a few years ago. When you're talking about the neural networks with the n-ary neural networks, can you talk a little bit more there? Unfortunately, you had to go quite fast there about how you're implementing that, what kind of database technology you're using, and what your thoughts are on developing that for the future.
Yeah, thanks a lot for that question. So the data here, what we did is we built some synthetic data. So what we did, we generate places from, I remember from DBpedia, and then we computed their relation. We sampled some relationships from that kind of data sets, and then use that as training. So that's where the data comes from. And for the model here, that actually this specific baseline model called n-ary neural network is from computer scientists. They built this model. We replicate their codes. But for the part that I mentioned, that we build a spatially explicit machine learning on top of that, for that actually we basically write our own code and write our own programs, and then build this and then compared our results with theirs using our own data sets, which is basically on places.
Okay, great. Thanks for explaining that. I think if I can follow up with a related question, but it's going to go off in a very different direction. You talked at the beginning about image schemata.
Yeah.
And then when we come back to here at the end, can you say a bit more about how image schemata are related to these concepts that you've been sharing with us at the end about qualitative, spatial, temporal?
Yeah, great question, actually. So I'm actually waiting for these kind of questions. So to be honest, I don't know the answer, but I have this is some work I really wanted to delve into. But I feel like, image schemata provide us some theoretical guidelines on how concepts are comprised. So I believe using the technique such as knowledge graph, for example, we can probably and combine that with some machine learning or graph techniques, we can probably detect the patterns from the data, and then maybe see how these kind of detected patterns align with the image schemata. For example, whether we can find some in graph theory they call it simplex, right? Whether there's a specific configuration of nodes and edges, and then they have this kind of container meaning. So that we can use this kind of patterns we learned from data coupled with the image schemata for later knowledge graph embedding work. Meaning that while we compute embedding for the nodes and the relationships, we are not only considering their pairwise relationships, we are considering the whole concepts altogether, which might be container, which might comprise of 5 nodes and 4 edges.
Interesting, very interesting.
So I see Simon have a problem. Have a question.
Yeah, I see Simon's first, and then Yano after that. Simon, please.
Hi, Ray. Thanks a lot for the talk. basically you discussed the different ways how you could go from geospatial or cognitive theories to GeoAI.
Yeah.
And in your examples, you mentioned actually sampling was one of them, and the other one was basically changing the architecture of these
right.
embedding models, right? So I was wondering actually what you think about, isn't there a third one, namely the possibility to instruct foundational models via prompts, right? Explicitly in terms of the models themselves, instead of just sampling, doing some kind of resampling or providing some kind of data to these models, but rather really instructing them directly with knowledge, top-down knowledge of the models that we have. What do you think about that?
Yeah. So very good point, Sam, actually. So at the end, they are all the same. We wanted to inject our inductive bias, which is top-down series, into our models. And the one I proposed here is more, going to their data and trying to inject our series, or going to our data structure, injecting their series. But I agree with you, probably for foundation models or for ChatGPTs, probably we can go the other direction, right? Like from prompt engineer perspective, like teach them or fine-tuning them. While doing fine-tuning, we inject the specific spatial series or geospatial semantic series. I haven't tried that, but I think that's a really promising direction. Thanks for mentioning that. Yeah, thanks.
Thank you, Simon. Let's see, Jano, you've got a comment or question here?
Absolutely, yes. And Ray, such a wonderful talk, such a tour de force over the last 20 years of semantics research, both very exciting and also maybe a little bit depressing. But what I think is interesting is that a lot of the work that you have shown shows our community's idea that intelligent systems will be like humans, right? And therefore, ideally, we would use metaphors that we know from humans and human thinking on a cognitive level, not necessarily a neural level, that would make better systems to support interoperability and so on. But what we are seeing right now is not that, right? We are seeing AI as a very different beast. For instance, very intelligent systems, compared at least to what we had before, whether they're truly intelligent is to be seen, that don't require consciousness, that don't require being human-like, right? Yeah. So what does this do to the first half of your talk? The later one, especially Link's work and so on, I can clearly see where this goes. But our wonderful, beautiful ideas, are there more than thought exercises by now?
So yes, thanks, Jano. So the first half of the talk is basically I wanted to reflect on our series. The very valuable series has already developed by our pioneers in this field, in this community, and highlight that they can be useful, but we haven't used them yet. And I agree with you. Right now, most of the AI are not human intelligence. They are mostly artificial intelligence, not human intelligence. And but whether we will achieve AGI at the end, that is still a question. And from my end is like we can't achieve AGI just feeding bunch of mass data sets into model and just increase the volume. I believe if we want to achieve AGI, we need these types of series. We need this type of domain knowledge. And to prove that they can really do reasoning, not exactly same to human beings, but similar. But right now, I believe at least as what I tested from the ChatGPT or other types of foundation models, they are mostly they are based on huge data, based on they are fluent in terms of natural language, but they don't know how to reasoning. And I think this is especially true for our domain. And because all these kind of spatial relationships, if you tune them a little bit and asking the system, they definitely won't get it right mostly. So that shows the limitations of the current AI. So I think one solution for them is to really introduce those work we have already developed in 1970s, 1980s, 1990s, like the image schemata, conceptual neighborhood, this kind of work, and try to incorporate it into our knowledge graph. But again, I'm interested on this, and the reason I mentioned all this work is to bring them up to our community. Hopefully, we can all work on this together, and I think they are valuable. And sometimes they are, especially in my generation, or my peers are surrounding me who are doing AI. I feel this is a problem right now. Is that we always forget this kind of series. We forget them. We always all go together with the fancy computer science methods without taking care of this kind of series. So that's the reason I wanted to bring them up here.
Right.
Yeah.
Very nice, Rui. Simon has another question, I believe. I can turn it over.
Yeah, if it's possible, I would just want to add to this, because I think this is a very important point. I really agree, very much agree with Ray there. And I kind of disagree with Christoph's statement there, because I think the main point that is overlooked there all the time, at least as far as I can see, is the issue of validity. I mean, these models are all very impressive and scalable and generalizable to some degree, but the issue is, in the end, in order to find out whether they are valid, you need to basically have one of those models, right? For example, in order to find out whether you have a representative sample of, for example, your spatial relations here in terms of in terms of your RCC8 model, you need the RCC8 model itself in order to pick out negative examples, and there you make use of the a priori knowledge. So the issue here is that once you want to find out whether a model is valid, you need to go back to the conceptual model, and you cannot do with a data-driven model alone. That's my point there that I wanted to add.
Thanks, Simon. Maybe Jano, you wanted to respond to that, or any further?
Yeah,
thoughts?
first of all, Simon, I always love to disagree with you, and there's just not enough time these days for this. There's always these wonderful talks right now, and then the discussion starts, and then the teleconference is over, and all the interesting stuff is never going to happen, and we would need like 1 more hour now to get into a good brawl. And I wasn't saying, Simon, and I'm the least one to say this, that it doesn't need theories. You know that I'm not a believer in this. But I do think that drawing them or basing them on cognitive models of the human mind and the human brain may not be the most successful path forward. Already the cognitive scientists are struggling with this. And right now, I'm not saying this is going to be like this forever, but the neuroscientists are running circles right now around the classical around the classical cognitive scientists, not saying everywhere, not saying forever, but right now we are in this dynamics. So do we really need to base our views of what GeoAI should be on cognitive models of the human mind and the human brain? This is not whether it needs theory. I absolutely agree it needs theory, and you gave a wonderful example. I'm just referring to some of this, what I think, wonderful models of image schemata, but we don't even know whether they hold from a neurocognitive perspective, right? And we don't know it at all, whether they're useful for GeoAI.
Mm-hmm.
Good point, yeah.
Yeah, thanks for that. Anyone else want to join in the discussion? Otherwise, I can do that. I think, to my understanding, it would be interesting first to look at the relationship between image schemata and cartographic representations, especially the interactional aspects of cartography, which have since Bertin remained underexposed and underconsidered. But it would be also, I think, interesting to, and I think I put a note to that, is to not look at these approaches as offering us the solution to the challenges of working with different approaches to different theorizations and different methods, but to see them as complementary and to assess to what degree the newer approaches can offer us another perspective, one way to put it, or perhaps a type of triangulation that could be used between different theoretical approaches and different methods to be able to advance particular application domains. I think you have here the small Lang model, which is actually a nice French spelling of Lang, but I won't go into that right now. But it would be interesting, I think, to pursue that kind of idea more with the geospatial context and relate that also back to cartography, the other fields. Jano, yeah, I'm never as sure if I'm as depressed by the last 20 years, but I hope that, the wheel keeps on turning, and that's what I really like. I'm really happy to have this exchange too, to be able to help move that wheel forwards. Well, I might have said the last words, I'm guessing. Looking at the clock and looking also that there's no other comments, I'm just going to do a last call in the spirit of what we heard, that we, really like to have these exchanges and engagements. I want to thank everybody for joining and taking part and sharing. Again, the presentation and this discussion will be online, and you can pursue it further there. And please, of course, contact Rui. And of course, the very, very big thanks, Rui, for that wonderful presentation and the great ideas you've brought into the discussion tonight. Thanks, or today.
Thank you so much for having me.
Yes. Okay. Well, everyone have a lovely day still. And again, hope to see you on the 5th of February. Until then, bye-bye.
Goodbye.
Bye.